Thank you, Mr. Chairman. So I'm not quite sure how I get this transition from the previous presentations about flexibility and especially a conventional power plant to my presentation, which is basically different. It's different in terms of, we have heard a lot about power system, transmission, connection to transmission system. Now I want to go into the distribution system, A, and secondly, conventional power plants versus now PV storage I want to look at. Nevertheless, I would like to take you on this journey into this distribution system and give you some presentation, some information on the SNOOPy project. It stands for Smart Network Control with Coordinated PV Storage, INFEED, and we have done this together with a distribution system operator in Germany, together with KTH in Sweden, and Fronius, who is a battery and inverter manufacturer, was sponsored by the German government. So what's the background about it? We have determined that in distribution grids, as soon as we add more and more photovoltaic into the system, we do face certain challenges. A, overloading situation could occur, but what we have observed mainly in this distribution system, we are looking at where we do our studies, overvoltage issues. So that's typically what we see in rural areas. And we are looking into the low voltage system. So again, power, that was like extra high voltage where we look. We are looking into the low voltage, or as you typically say here in India, low tension system. So what's the issue? Basically, as soon as we add lots of photovoltaics feeding into the grid, we do get a reverse power flow. And with this reverse power flow, we can get overvoltage issues. And the idea was now to find a device which is actually then improving the situation and allowing for more photovoltaic to be integrated into the system. We called it SNOOPy, mentioned earlier the name, or SNOOPy box. And the idea is basically to control the voltage and to do it autonomous. So no real communication, that was the main idea, and it should be transferable. So we use the SunSpec protocol, which is then communicating with the inverter. So it's applicable to almost any PV or battery inverter. We are now in the more or less final phase where we do the field tests. Don't want to go through all these phases we have been done so far, like the development, and the project will end next year, hopefully, and quite sure about that, successfully. So one main idea behind it is actually to use a QU characteristic. You might have heard about that before. It's one of the possibilities you can program an inverter. So very standard is a constant power factor, or cosine phi ending, changing the power factor according to the active power output. And one very common possibility is a QU characteristic, so providing reactive power depending on the voltage. So that's what we have used, but the question is, how do you set this? And we decided that we want to have some intelligent algorithm which is actually setting it coordinated. So that's why, one of the reasons why we called it coordinated INFEED. So this coordination of all inverters is basically done in a manner that we have a self-learning algorithm implemented, which is then determining the maximum voltage, which is at the various locations where the PV systems are located. And the idea is to activate all of them more or less at the same time. And I will show you, at least from a simulation perspective, how this works. The second option or possibility we wanted to implement is the question, what happens actually if you change the grid topology? Yeah, so that's quite common, at least in Germany, but from time to time you want to actually switch like feeders from A to B. And now the question is, what would our system do if this is the case? So first of all, it determines, our system would determine the maximum voltage it sees. As soon as the location of the PV system, of the PV battery system, is now at the end of the feeder, so there it actually then sees a higher voltage, that's no problem because it will then adjust further. But what happens if it comes to the beginning of the feeder and it has now lower voltages? I will explain this a bit more in detail later on. And so we have used some algorithm in order to determine what is the new maximum voltage you would actually see. And that's what we do by determining the sensitivity of the voltage based on Q. So we change the Q a bit and see what happens to the voltage. The second, so I'll be talking about reactive power, is active power. Active power, control of the battery. So we're talking about, we've heard the behind-the-meter batteries, basically, PV storage batteries we're talking about. And what we see in Germany is the reason for getting batteries into the system is mainly with regard to self-consumption. So new PV systems are are coming actually together with a battery. And on the left-hand side, maybe I can show this. On the left-hand side, you can see the typical characteristic, what happens during a bright day, low load situation. If you want to improve your self-consumption, that you would actually then charge in the very beginning, in the morning when the sun rises, and your storage will typically be full already maybe at 10 o'clock or something. So the peak of the PV system would then feed into the grid and therefore be not really in favor of the grid, so would stress the grid itself. So the better solution would be to do PV peak shaving, so to store the energy or the PV power then during midday. And the question is, how can we do that? How can we then coordinate all PV systems to do this? And that's what we also, it's one of the features which we have implemented. And to do this, we need to have some kind of forecasting. We used a persistence method to do so, and we used like we wanted to keep it simple, basically. We didn't want to have any, don't have any communication, so we can't really look into the internet and see, okay, what will be the weather tomorrow. So we took a persistence method. We know what happened on the very same day, and we need to determine 3 values. A, the generation peak, what we do expect. Second, the time of sunrise, and third, the time of sunset. And from this, we can actually using a sine wave, determine very well the maximum. On the right-hand side, you can see how this works. So this is a real PV output of a system in Germany, and we were able to detect this pretty well, the maximum value, and especially also the sunset and sunrise values. So next step we have done is we have simulated, we put a model in Dick Silent Power Factory of the area. So it was the low voltage area, a couple of feeders there in close to where we are located in Germany. And we applied our algorithm, it was programmed in Python, with an interface to Power Factory to determine and to develop the model strategy. After that, we just exchanged the interface to, instead of the simulation model, we connected our battery inverter in the lab and just did more or less the very same. So to call hardware in the loop, if you could call it like that. And now the next step is to go into the field. So we have 7 battery systems now equipped with our Snoopy box, and they are located in the field. So you can see here the sketch for that, and that's how it looks like, just a small box where the intelligence is inside. And I think more interesting is actually this area. So you can see the feeder. This is the substation. Can you see this? Yes, the substation where you have feeders. And we have seen that on these feeders there are actually voltage. There's a very high penetration in this area. So lots of rooftop systems already included, where the voltage is actually then varying between 0.93 per unit and 106 per unit. According to the standard, it should not be more than 1.1 per unit. So as soon as there are coming a couple of more systems in there, there will be definitely an issue in this area. And there we have some battery locations here, and we also added a couple of power quality analyzers and phasor measurement units in order to see what is the impact of the battery systems and our control on this low voltage system. So here you can see some simulation results with regard to the learning behavior. So within a couple of days, we can actually determine the maximum voltage which is observed, and this is so very clear, and then it's very steady. And on the upper side, you can actually see the dependency of the voltage on the Q. So for this, if the Q is changing, what is the voltage changing? That's how it is then implemented. And from this, we can determine these kind of QU controls I have shown to you in the beginning. So typically, you have a certain dead band where you don't want to do anything because reactive power does normally then, or this also introduce additional loading and losses. Therefore, you don't want to do it. You just want to use it when you really need it. And these, like this orange one here, is a location which does face only lower voltages. That's shown here. And that's the voltage up here. And therefore, we asked it to act earlier, so at lower voltage levels in order to provide reactive power and to support the system. Whereas these two, like the bluish and the purple voltages are much higher, up to 1.06%, I mentioned earlier. And we implemented these characteristic for Q. And you can see on the right bottom now that they are actually synchronized. They're not perfectly synchronized. I mean, right? Not perfectly synchronized, especially the orange one, because you have like not a perfect voltage profile, so in terms of coordinated voltage profile, but it is definitely according to our expectation. So what happens if there's a switching happening? So here's a switching happening, and what we do is basically we reconfigure, recalibrate the U and the Q. That's here. So here's the calibration happening. So you can again see that's working quite fast, and also the maximum voltage. In terms of voltages and reactive power, you can see this quite nicely here. So here, 27 June, there's a switching happening. After that, the voltage is much lower, and my system is not doing any reactive power control anymore. So we can determine this, and then we do a calibration, as been shown here, and then from there on, reactive power provision is continued. So that works quite nicely. With regard to the active power, you can see that we have this peak shaving. At the same time, we want to, because it is behind the meter and is still the objective of the owner to have a high self-consumption, we said we want to not interfere into this. So the self-consumption should be more or less the same as if you have like this unfavorable control with regard to grid penetration. And you can see here 3 different possibilities. The blue one is if you have like perfect foresight. Obviously, you don't have that. The black one would be if you just do self-consumption optimization, so where you have really high voltage above 1.1 per unit. And the red one is kind of our control, which kind of a compromise sufficiently getting down the voltage at that point. And with regard to the self-consumption, as shown on the right-hand side, you can't hardly see it. There's a very, very small difference between the 2 lines here. So there's no major impact on the self-consumption, what we have determined with our algorithm. To conclude, by parameterizing this QU curve, we can like coordinate it, and this helps to reduce the voltage. Yeah? Secondly, we can coordinate it with regard to cutting the PV peaks in order to reduce the voltage, and it's at the same time also reduce the loading, because voltage and loading typically have very high correlation in this feeders. And by using these sliding prognosis, as we call it, or persistence prognosis, the self-consumption itself was hardly affected. So we believe that this box can be used by distribution operators, for example, into the system, and this have a lot of benefits because it is in a coordinated manner, and therefore allows for integrating more PV into the system. What is with regard to India, I have learned a lot in the last year about the Indian power system, especially this distribution power system. There's one major issue as well, and we heard it like last day and today as well. That's the evening peak, and having like batteries included here, also with such a system that could be a coordinated manner be used to also shave the load peak, the consumption peak in the evening. That's all from my side. Thank you very much. Thanks.